Geometric varying motion is a continuous time stochastic process in which the logarithm of randomly varying quantity follow a varying motion. In particular, it is used in mathematical finance to model stock price in the Black-Scholes model. Modern mathematical economists usually prefer to use geometric Bn over Bn as a mathematical model for asset price with the assumption of their constant volatility. In an economic situation, there is always a factor of uncertainty. A form of workable hypothesis is required in order to choose the right investment and business strategy. Based on this article, there are some issues, such limitation in ability to borrow for the purpose of investing a risky asset. Hence, this study is to solve the optical dynamic trading strategy for investors that face a leverage constraint. A second constraint is the requirement that investor will be non-negative at all times. Therefore, BN and geometric BN will be modeled. So let you see if this model is suitable to be used in mathematical finance, and this method can be used for forecasting and solving financial problems.
For geometric BM fundamental, it is used to model stock price over time where the percentage change are independent and identically distributed. Zt is geometric BM that equal to Z multiplied with exponent to the power of mu t plus sigma bt with the conditions stated above. Next, the mean and variance of geometric Bn is Z multiplied exponent to the power of alpha t and Z square multiplied with exponent to the power of 2 alpha t minus 1. Next, for stochastic control, suppose that a person has two possible investments. Firstly, a risky investment, example stock, where the price P1t satisfies the stochastic differential equation. Next is safe investment, for example bond, where the price P2t grows exponentially.
In finance, geometric BM process implies that the asset return is normally distributed. So we model the low return with asset price S at time t is st. By using the condition of asset return, we get this equation where z is 10 dBm. As example, since the value of money in the future always change, so we examine the probability that on barrier is by a future time where the barrier h below the current price s and the future timing t is larger or equal than t. The relationship between the current price and the terminal price is st equal to s exponent h less than h. By using log, we get s equal to log h over s, where s is normally distributed by mean mu t and variance sigma squared t. The probability that a barrier can be written as t. So in this situation, we want to know whether zt is a barrier b from above before time t and written as this. Then we can get the probability like this. Thus, the drive case is 0 and finally we obtain like this.
There are a few situations we can discuss. Firstly, when the stock price below h, with the h is the barrier, we get the equation 1 at time t. We also show that if none hit the barrier, we get the equation 2. Second situation is when the price stock do not stop at the barrier and the price can be more than the barrier, we get the equation 3. In the third situation, show the Black-Scholes formula, equation 4, then become equation 5. The situation is when the price stock is hitting the barrier, we get the equation 6. 1 minus is the probability of ST hitting the barrier. The formula 7 is from the Black-Scholes formula. The Black-Scholes formula is R minus alpha squared over 2, but in the log return, the drift term is mu t. Therefore, probability of ST smaller than H is similar to the Black-Scholes formula. If H were the exercise price, the above would be analogous to 1 minus ND2, or the probability that the call would not be exercised. For the log return cases, we get the equation 8. Then, by the log probability, we simplify this into equation 9. If the asset driven 0, this expression will be simplified to the result we obtain when specifying the probability for Z hitting the barrier.
This research is constructed to apply the geometric Brownian motion into the log normally distributed asset return. As for the ideas, the authors drafted the example situation of the investment possibilities in kind of stock for risky investment and bond for safe investment. For the main focus, which is the application of the geometric Brownian motion into the log normally distributed asset return, the author drawn up another example situation of given condition asset with a barrier as the limit for the option. Then, the probabilities of the barrier being hit or not is determined by the implication of the geometric Brownian motion into the log normally distributed asset return. Hence, it can be concluded that the geometric Brownian motion is useful in modeling of log normally distributed asset return and stock price over time, as it will assist the investor in making a decision.